Hello, a very warm welcome to this video. So this is just going to be a light video on what is functions. I'm going to be talking about what is a function. If you've seen my channel before, I've done a lot of things on mathematics, physics, and one of the foundations of these things are functions. So I'll be talking about this in this video. In coming videos, I'll be doing a lot more on the spiritual side of things. So a lot coming up on this channel, but for now, let's have a discussion of functions. So let's begin with talking about what a function is. And as always, we have to begin with a rule, some kind of definition. And this is if capital A and capital B are sets, then a function from capital A to capital B is a rule which to every element x in capital A assigns a unique element in capital B. And this is rather abstract and not very clear really until we show it visually. So that's considered two sets. And they can be linked with a function f. And these two sets are represented in two kind of elliptical blobs, if you like. So in my first blob, we have set capital A, which contains three elements, which are A, B, and C. And in my other blob, we have set capital B, which contains elements x, y, and z. And f is any function which, to every element in set capital A, so that is to elements A, B, and C, assigns a unique element in capital B. So the easiest and simplest kind of function we can have is a bijective function. And this just has a one-to-one correspondence where we have arrows essentially just going from one element to another. And this is an example of such a function. So here we can see that all elements in set capital B, so if you like, our outputs of our function, all of them have an arrow going to them. So we call this a surjective function. Also, the arrows going from set capital A don't branch up for when they go to set capital B. And also, so this is a function, but also the if you have two elements in set capital A linking up to the same element in set capital B, so we call this a injective function. And because this function is both surjective and injective, we call it a bijective function. And the cool thing about bijective functions is they have inverses, which I'll be coming on to later on. But we can see that this is a function because to every element, capital A, we have a unique assignment in set capital B via this function. So let's look at another function which is neither surjective nor injective. So it's not a bijective function, it doesn't have an inverse, but it is still a function. This is a bit cool, so I put the definition up there for just reference. And we've got our sets, and this is also a valid function. Now, this is not a surjective function because we have a label y, an element in our output set, which doesn't have an arrow going to it, and therefore this function is not surjective. And this function is also not injective because we have two elements, A and B, in our input linking up to the same element in our output. However, this is still a function because A links up with a unique element. So small a in our set capital A links up with a unique element in set capital B, that being x. Same for B and same for C. So we have a unique element assigned for each of our elements in our initial set to our output set. So this is still a function. However, if we're going to invert this, so we're going to flip over the arrows to try to create an inverse function, well, then we'll no longer have something that can be classified as any kind of function, so this function does not have an inverse. And that's because if we try to invert this, we've got two problems. Firstly, set capital B, which now becomes our input, well, we're going to have a variable y in set capital B, which doesn't have an assignment in our output set. So it's not a function, and also we get the input variable x, which goes to two outputs, both A and B, in our output set. So we no longer have a unique assignment because that has two assignments, not a unique assignment, and therefore we clearly cannot have an inverse function. So this is not an inverse function. This is not an inverse function, and the thing about this is we flipped a function, and we've got something that you might think of as being an inverse because we flip the arrows over, but it's not an inverse function because it doesn't satisfy a definition for what a function of any kind has to be. But if we go back to our one where we had a bijective function at the beginning and just flip that to get this, well, this clearly is an inverse function. And the kind of thing about inverse functions is they reverse what a function does, and the reverse still satisfies the definition of a function. But because they reverse it, if we operate an inverse function on the output of our function, we get the input we began with. So if we have an input theta, then f acting on f to the minus 1 theta is theta. Let's take x. So if we operate f to the minus 1 on x, we get a, and then if we operate f on a, we get back x. So the inverse of a function essentially undoes what a function does, and that's a visual depiction of what an inverse function is. So an inverse function is what we get when we flip over the arrows of a function and we're left with something which can be still thought of as another function. It satisfies the definition of what a function is, but it undoes what our initial function does. So that's what an inverse function is. Now let's talk about composite functions, because they're often something people find confusing. I'm going to show you that actually we can think about them very straightforwardly. So let's start with two sets, and let's bring in another set. And let's have two functions. So function f links a, b, and c to x, y, and z, and then function g links x, y, and z to these Greek letters, which are delta, beta, and mu. And the thing about a composite function is it just binds these two functions, f and g, together. So let's talk about this equation, which is appeared on the bottom of the screen. So f acting on a brings us to x, as we can see via the white arrow, and then g acting on the output of f acting on a, so g acting on x, then brings us to delta, again via the white arrow, and so g acting on f of a equals delta. So essentially a composite function is just linking these functions together and saying, well, we can treat the output of one function as an input of another function. So if we act f on a, we get x, but then if we act g on x, we get delta. So if we acted g on the output of f acting on a, we would get delta. That's all a composite function is. It's just binding two functions together. And this really summarises our discussion of functions and what functions are. So now I'm just going to briefly mention what's coming up. So on my channel I do a lot of things on spiritual stuff, so I'm going to be talking more on the demonic things. I've done a couple of videos on Belial and the Leviathan, so I'll be doing more videos on that kind of thing. I'll be doing a voiceover perhaps for ASMR, the Satanic Bible, also be doing CTA implementation. But this has been a quick tour of functions. I really hope you've enjoyed this video and it's helped seeing it more visually. Please check out my channel for more, and please like or subscribe if you would like to see more, so you get notified when new videos coming up. Thank you very much for watching this video.